Assalamu alaikum. Hello everyone. This is Mehdi Hassan Chaudhuri. My ID is 224080002. Today I am going to talk about software architectures for embedded systems, how software is organized in small devices and why it matters. We'll start from simple round robin architecture and then moving towards function queue scheduling, and finally we'll talk about real-time operating system architectures. We'll also touch embedded program modeling and software development processes in embedded systems. So without further delay, let's get started. So let's start simple. The round robin architecture. The system just checks for device one by one. If a device needs service, it handles it, then moves on. So here is no scheduler, no priorities, just a loop. It's easy to implement, low on memory, and easy to debug. But if one task takes too long, everything else waits. Urgent events get delayed. It's basically good for simple, non-critical systems. So here its advantages. It's simple, no interrupts, minimal memory, but its disadvantages is it's slow for urgent tasks, no prioritization of tasks, adding devices can break timings. It's not suitable for critical time critical applications. It's best for simple system with non-critical timing requirements. Function queue scheduling improves round robin. Hardware events trigger an interrupt which quickly adds a function to a queue. The main loop then executes those functions. This keeps interrupt fast and heavy processing happens safely in the main loop. It's better than round robin, but still not perfect for critical deadlines. So basically, how it works: ISR handles urgent hardware tasks quickly. ISR adds functions to the functions pointed to QA, main loops DQ, and executes the function. So its benefits: it's faster response, flexible, interrupts stay short. And if we talk about limitations, QE can overflow if overloaded. Shared data needs protections. Still not full prioritization. Its key challenges is managing QA size and handling overflow conditions gracefully. So now we'll move to the next architecture, RTOS architecture. An RTOS is an operating system designed to handle real-time applications with deterministic timing constraints. It has a kernel, a task manager, a scheduler, and synchronization and timer services. So kernel basically core scheduler managing task execution. Task manager creates, deletes, and manages tasks. Scheduler determines which tasks run next. And synchronization, semaphores, mutexes, message queues, timer services, delay functions, and timeouts. So high priority tasks can interrupt lower priority tasks immediately. It also includes semaphores, mutex, and timers for synchronization. This ensures deadlines are always met. Tasks move between running, ready, and block state. So RTOS tasks have three consecutive states: ready, running, and blocked. And different scheduling algorithm used for managing these states, like rate monotonic or earliest deadline first, which decide task runs next. This makes timing predictable, something simpler systems can do. Move to the next. So why model? Before coding, we need model. UML diagrams, state machines, and flowcharts helps us visualize behavior. For example, a simple state machine moves between idle and active states on events. It helps catch mistakes before coding. So here are some common modeling techniques: UML diagrams, state machines, flowcharts, data flow diagrams, etc. So here are some program modeling for multiprocessor system. So in multiprocessor system, the major challenges are task allocation across processors, inter-processor communication, synchronization and shared resources, load balancing. Modeling approaches: MARTE profile, deployment diagrams, communication diagram. In multiprocessor systems, complexity increases: task, communication, synchronization, and load balancing. We use MARTE, deployment diagrams, and communication diagrams to plan behavior and timing. So the key consideration is model both functional behavior and timing constraints for accurate analysis. If you just model functional behavior but avoid timing constraints, then it will not work properly. So the V model is a software development lifecycle that emphasizes verification and validation at each phase. It has two sides, as we see, left side and right side. In left side, there are requirements, system design, architecture, implementation. And in right side, it's testing part. So there are different types of testing done, like acceptance test, system test, integration test, and unit test. It goes from lower to upper. So implementation after implementation, we should unit test, then integration test, then system test, and finally acceptance test. Each development phase has a corresponding test. Like requirements has acceptance test, system design has system test, architecture has integration test, and implementation has unit test. So here are some specific testing methods. Specialized testing for embedded systems. Model in loop, or MIL, test algorithms in simulation. Software in loop test generated codes on host computer. Hardware in loop test with simulated hardware environment. And field testing test in actual operating environment. Safety standards like ISO 26262 for automotive systems, IEC 61508 for industrial control, and DO 178C for avionics make sure systems are reliable. So here is a comparison of architecture. So round robin, if we talk about round robin, it's simple, low memory, slow response. And in case of function queue, it's a better response, basically. Limited priority, it has limited priority. Prioritization is limited. In case of RTOS, it's fast and scalable, full prioritization. So selection criteria, if we have a simple non-critical system, then we should use round robin. For moderate complexity and interrupts, we'll use function queue, and we'll use RTOS for complex time-critical applications. So here is the summary of today's presentation. So So round robin is the simplest architecture but lacks responsiveness. Function queue improves response time by deferring processing. RTOS provides full task management with priority scheduling. UML and MARTE are essential for modeling embedded systems. vModel ensures systematic development with verification at each phase. We should choose architecture based on complexity, timing, and resource constraints. Okay, so thank you. That's all from my presentation. Thank you, everyone.